Oh shoot, hey, if you can't tell what the title of this lesson is, let me turn that upside down. I had it upside down, sorry about that. Let me just flip this around. There you go. Now can you read it? Oh, hold on. It says the same thing. Yeah, symmetry. Is that pretty cool? So symmetry, it's found everywhere. There's three different types of symmetry we're going to look at. The first one's line symmetry. And line symmetry is when a figure has a type of symmetry where a line could be drawn through the middle of that shape and each side is a reflection of the other. Notice with this arrow icon, I can draw a line through it, coming right through the point, and I get this mirror image of itself, where if I were to fold along that line, I would fold it right on top of itself, and that line is what we call the line of reflection. So line symmetry is when there is a line of reflection. And I love this example. This is from Scott Kim. It's a mirror. The word, of course, is mirror, but the best part of it is there is a mirror. Basically, this has a line of reflection right here down the middle. So that's pretty cool. And line symmetry is found all over the place, particularly in nature. This leaf here and other things have this, what we call bilateral symmetry. In science, in math, geometry, we're just calling it line symmetry. If you can draw a line down it, cut it into two equal halves that could be reflected onto each other, you got line symmetry. Pretty basic. Now the next kind is called rotational symmetry. And in rotational symmetry, we will, like the name suggests, be rotating. So the shape can be superimposed upon itself. In other words, it can be moved and land right back on top of itself with a rotation of less than 360 degrees. So as long as I can turn it and I don't have to make a complete turn and I can land it right back on top of itself, it's got rotational symmetry. Now, as we use rotational symmetry, we refer to two things about that rotation that helps us to understand that symmetry. The first one is order, and you'll want to get this down. Order is the number of unique rotation angles that superimpose the figure upon itself. Now, that is a really long way to say what we really mean, which is that how many different positions can you turn it into, and it still looks the same as it originally did. For this one, the order here would be 3, because I could turn this into 3 different positions, each time just bringing another piece up to the top, and it would still look like it did originally. So that's the order. We'll look at a couple examples in a minute. And magnitude is really closely tied to order. Magnitude, jot this down, is the smallest possible angle measure that superimposes the figure upon itself. So how many degrees do I have to turn this in order to make it look just like it does right now? That's what we call the magnitude. And with something like this is probably going to be about 120 degrees. I'm going to have to turn that. Again, we'll take a look at that. So in nature as well as in design, this is a quilt pattern. I love quilting. You see this different types of rotational symmetry. And each time you look at those, there's always this center of rotation. You're going to just turn it a different number of degrees depending on the order you've got. And then the last type of symmetry is called translational symmetry. And this one's pretty basic. An object has translational symmetry if the pattern superimposes onto itself with a simple slide or translation. So this wallpaper pattern here, you just slide it up a little bit or slide it to the left or right, and it's going to look like it does right now. That's translational symmetry. A honeycomb's a great example. As we see these different hexagons all in a row, we could slide across horizontally. We could slide even on this diagonal. And this is one of my favorites. This is M.C. Escher. You've seen some of his work before. I want to enlarge this one so you can get a better look at it. All these Pegasuses, how do you say that? Anyway, are they white or are they brown? Well, it depends on the row you're looking at, but each one is a translation of another, and so that's got that translational symmetry. Love M.C. Escher. Look up more of his stuff. So a couple things you'll be asked to do. One thing you might be asked is to find lines of symmetry for things that have that line symmetry. So where could these lines of symmetry be, or where are these fold lines? Well, does this one have any? At first I thought that it didn't, and then a student pointed out to me, yeah, you can go right through the center this direction, a horizontal line of symmetry, and that cuts not only the circle but also the 3 and the 0 right in half. So there's one line of symmetry for that one. How many are there in this sign? Draw all the ones you can find. In this case, there's just the one coming right through the nose of the plane and out the tail right here. It also splits that triangle nicely into 2 equal halves, folded on top of itself, if you can imagine it. This one, where's its line of symmetry? There's only one in this case. Right there. How about the cow? Well, the triangle itself has a line of symmetry, but if I try to draw it through, it splits the triangle, but it doesn't split the cow. So overall, that design does not have any symmetry at all. Let's erase that line. Okay, next one. Now this one, how many lines of symmetry does this have? Why don't you pause the video and see how many you can find? How many did you get? I counted 3. Let's take a look at where they are. Now, you have to come through that triangle. So here's one, and it splits the not just the triangle, but the snowflake in half. There's another one coming right vertically through here. And then a final third one coming through the diagonal on the other side. So those are my 3 lines of symmetry. And this last one, where are its lines of symmetry? Well, you might think we might be able to split that right down the middle. No, we can't, because those arrows aren't pointing with that fold symmetry. So this one doesn't have any. So with that example under our belts, let's tackle the rotational type of symmetry. In this example, we're going to do 2 things. We're going to determine the order of symmetry and the magnitude of the rotation. So the order of symmetry, look at the figure and ask yourself how many different positions can this figure take on and still look just like it does? Well, one way to do that is to count the repeats in the pattern. I'm counting here these petals. There are 5 of them, so any of those petals could be at the top of the picture at a time. And that means that the order of this symmetry is order 5. Now the magnitude of rotation would be how many degrees of rotation do I have to make in order to turn that so that this petal does come up to the top? How many degrees is that? Basically what you got to do is think about where the center of that rotation is and the fact that you are going to be rotating through this size of an angle. And if we were to extend that out, each of these is dividing this into equal parts. So it's a pretty simple formula. If the order is 5, then I'm going to take 360 degrees for an entire rotation and divide it into 5 equal parts for an answer of 72 degrees. That's what I call my magnitude of rotation. So it would take 72 degrees to turn the flower and superimpose it back onto itself. Let's try this one. So what's the order of symmetry here? First of all, how many repeats do we see as we see this turn happen? The repeats are happening with those arrows. So there's 1 there, there's 2 there, and there's a third one. So the order is simply order 3. We have order 3 symmetry. Now how many degrees of rotation does it take to turn one arrow onto the other? And I'm going in the counterclockwise direction, pretty standard with math. It really doesn't matter, but I'm going to take 360 degrees total, divide by the order 3. That gives me my angle measure. So it's 120 degree rotation. So symmetry is pretty cool, and you see it everywhere, even in people. You know, they say that people are symmetric, that we could draw a line symmetry. We could draw a line right down the middle of our face. And we could, hate to do this to you, Mr. Newman, we could get 2 equal halves. And, you know, they say that you could split yourself and you could just copy your left side onto your right side and look just the same. I'm going to leave it up to you to decide if that's actually the truth. Good thing Mr. Newman's a good sport.